Okay, so hello, good morning, everybody. It's time to start the third day of this wonderful workshop. And our first speaker today is Thomas Weber from University of Bologna. So Thomas obtained his PhD in 2020 at the University of Naples, and his dissertation was about braided commutative geometry and Greenfeld twist deformations. And his research interest includes such topic like Hopf Algebra, so probably no surprise, as you can see the title of his talk already, but also representation theory, deformation quantization, Poisson geometry, and also topics more closely related to physics, like, for example, field theory, supergeometry, and renormalization. So, Thomas, the floor is yours. So please.
Thanks a lot, Adam. Thanks for this nice summary. I would also like to thank the organizers for setting up this nice workshop and letting me give a lecture about a topic that I really like, namely, as you heard, about Hopf Algebras. So the take-home message of this talk is probably that if you look closely, you can find them in all kinds of fields of mathematics. And so it is good to know what Hopf algebras are and that you are able to use them. Yes, so I will give you the basics on Hopf algebra theory. And at the end of this talk, or let's say the last half, we will see one of those unexpected applications. Namely, we will figure out that the forest is a Hopf algebra. Of course it is. Yeah. And then see how we can use the Hopf algebra structure of the forest to renormalize quantum field theory. And this last part will be just very briefly. I'm not an expert on this topic, but yeah, just to make you curious. Okay, so let's start. So this is an overview. So just broadly speaking, what is a Hopf algebra and why do people care? And with people, I should maybe specify mainly mathematicians and physicists. Maybe not everybody cares. So the slogan that one could give is this one here. So Hopf algebras correspond to symmetries in non-commutative geometry. They are quantum groups. And this is something that sounds nice, but doesn't have a lot of information. So we have to specify what we mean with this slogan. And also I, as a warning here, the word quantum groups is used by different people in different settings. We will later on see that quantum groups can mean different things. You have to be careful here, but just as a first thought on what a Hopf algebra is, you can think of it as a kind of quantum version of a group. So let's have a look here at classical and quantum picture. You can think of this as classical physics and quantum physics. So in classical physics, you might start with a manifold M, a smooth manifold, and look at the functions on this manifold. And this you might think of as your observables. On the quantum side, yeah, since quantum physics is pointless, you don't have a space in general. You can only work with the algebra. So here we start with a, in general, not commuting algebra. A, so just a vector space with some product M and some unit 1. And usually I ask this to be associative and unital. Many people might drop, let's say, the unital. So there are good reasons not to want a unit, but this talk will be very basic. So let's have a unit. And okay, on the classical side, you might have Lie groups, yeah, which people know, and what corresponds on the quantum picture is a Hopf algebra, I claim. Yeah. So then what can you do with Lie groups? You can act, you can look at the symmetries of your system. So here you have a Lie group action, while on the right side you have an Hopf algebra action. And now just a quick comment for the expert, you might say that the arrow goes in the wrong direction, because usually from if you go from left to right, you take the pullback functor. So this would mean that you would have an arrow from A to the tensor product. But the good thing about Hopf algebras is they are really flexible. And so you can also think of the left-hand side as a Lie algebra action. From the Lie group, you get a Lie algebra. Sorry, please. Functions, yeah. Yes. Mm-hmm. Yes, so this is what I'm commenting on now. I was saying that the expert might see, and I mean, you spotted it, there might be some problem here. The problem being that if you go from left to right, you would use the pullback functor, which means that the arrow would go the other way around. So your expectation would be that this right-hand side here is from A into H tensor A, but it is not, because so it can be thought in this way, but I'm thinking of it differently. I think of this Lie group action as a Lie algebra action via fundamental vector fields. And then you can have an action of the universal enveloping algebra that you might think of as invariant differential operators on your manifold. And then all of this makes sense. But this is just a toy picture, so it's not really a deep meaning. Yeah. Good. So this is how to think about Hopf algebras. To be a little bit more precise, a Hopf algebra is what is written here. So first of all, you have an algebra. You have a co-algebra on the same vector space. We will see in a second what this means. You have an antipode, and you have some compatibility of those structures. That's it. Yeah. Good. So before seeing the definition, let's look at the history. Probably the first formal definition of a Hopf algebra was given by Pierre Cartier in 1956, and his work was based on earlier work by Heinz Hopf in the 1940s. So the name that was given to this object was a hyper algebra, which I think is also a very cool name. But in the end, it was the name of Heinz Hopf that was given to this Hopf algebra, so, for his fundamental work on the subject. Okay, probably one of the first books to really make the subject into a popular one was the book by Sweetler in 1969. And it's a really nice book. Check it out. Many of the notations that he is using is still the same one we are using now. So he coined a lot of the notation in the field. Like for the co-product, people write this. We will later on see what this means. Okay, next, coming to probably the giant of Hopf algebras and quantum groups is Vladimir Grünfeld, who introduced the theory of quantum groups. And this is not only interesting for mathematics, but also very interesting if you're thinking about quantizations and mathematical physics. Probably
So in particular, it was Grünfeld who coined the name quantum groups.
Absolutely, absolutely.
Because Barnovich had this horrible idea of calling them pseudo groups.
Right, right.
So sorry, could you say a few words about the original motivation of Vladimir Grünfeld, coming from physics? But what was the dream of this approach?
So of course I don't know the exact motivation for the definition, but let's say that the quantum groups that he was introducing were Q deformation of matrix quantum groups or of universal enveloping algebras or classical Lie algebras. So he was thinking of this as some approach to quantum physics via a deformation parameter. This is just a very explain.
So this is some sort of generalization and quantization of infinitesimal differential invariant operator, something like that, yes?
Probably.
Okay, thank you.
Okay, and yeah, maybe the second giant after Grünfeld, was just mentioned by Piotr, is Bologna, who introduced compact quantum groups, and those are the Hopf algebras that are most suited for, so in the framework of C-star algebras. And here I'm a little bit vague. They are not really Hopf algebras, but they are having a dense Hopf subalgebra that you can work with. Okay, then let me also mention that Bologna introduced differential calculi on quantum groups. So he not only gives, but also classifies all possible differential calculi you can build on such quantum groups. One more thing that I would like to mention is Grünfeld and Majid proved the correspondence of quasi-triangular Hopf algebras and braided monoidal categories. So we have seen braided monoidal, so not braided, but symmetric monoidal categories in one of the student talks. So yeah, what this tells you is that if you are interested in monoidal categories, then you are automatically also interested in Hopf algebras. This is one of the instances where Hopf algebras just appear. And then latest from the 1990s on, Hopf algebras are commonly used in quantum differential and Riemannian geometry. And I just list some of the players here, but there are many, many more. Let me also say that all of this history is very biased. I'm leaving out many things. Yeah, I basically just list the names and papers that are important to me. That's why this is very biased. You shouldn't take it too seriously. Okay, here are some books that you might want to read if you want to learn about Hopf algebras. I'm not sure if you can read the titles, but so the first one here is the book of Riedler that I mentioned from '69, and it's a brilliant book if you want to find the first reference of some statement. In many cases, you will find it there in some kind of version. So yeah, it has many things. The second book by Montgomery, I recommend very highly because it's very fast. If you want to learn something in a very few pages, go to this book. But
you also have some Hopf-Galois theory there, right?
Absolutely. So this comes in the second half. You can also learn this, and it's written in a very clear way. Okay, the book I recommend the most is the third one from Kassel, Quantum Groups. So it's a beautiful book. I learned so many things there. And if you just read, let's say, the first 3 chapters, I think you have a very good understanding of what a Hopf algebra is. It's very well written. And then, okay, there are more books if you want to dig a little bit deeper. There's this one here if you're more interested in braided monoidal categories. And yeah.
Do you know why the color of his book is like this?
I don't know. Tell me.
Well, Sean told me that it's because he wanted his book to have such extremely outrageous color that everybody could immediately spot it on shelf. Okay,
nice choice. Yeah. So check out this book. I also recommend it highly. And okay, the last 2 books. So this one by Klimig and Schmidtgen is about representation theory of quantum groups. And the last one here, as I mentioned, of quantum Riemannian geometry is a little bit more difficult. So if you want to read this one, you should definitely first have a good understanding of Hopf algebra theory. But I also recommend it. Good. So let's come to the definition. So let's first talk about algebras. I guess most, if not all, people know what an algebra is. So just how to rephrase associativity and unitality of your algebra. And this can be done in a nice way via those diagrams here. So yeah, very simple. You take some element A, B, see here, you follow the arrows. So if you first go left, here you have A, B, C. You go up, you have A, and then bracket B, C. You multiply here, you have A, B, C. You multiply here, and you got A, B, C, and of course, those have to be equal. So this is just a diagrammatic way to write associativity. And in the same way, you can write the unit axiom. Yeah. So here, what is happening? So you have H here, which you can just tensorize with the complex numbers. This doesn't change anything. So it's just the isomorphism is given like this. So you have the 1 in C, you have H. You go up via this map eta. Eta is just the unit map. So as you can see here, you just multiply a complex number with the unit in H. So here you end up at the 1 in the algebra. Here you have H, you multiply, you have 1 times H, and identity gives you H. So this just says that H has to be equal to 1 times H. And you might ask why this complicated diagram if I just want to say 1 times H equals H. It's why should I do this? It's a good question. And maybe the answer is the following definition here. Because if you want to know what a co-algebra is, you just take the diagrams here and reverse all the arrows. So you can see the diagrams are really the same, just going in the other direction. And this tells you what a co-algebra is. So a vector space H is a co-algebra if I find C linear maps from delta from H into H tensor H and epsilon from H into C, such that those diagrams commute. And you can see it's really just the opposite direction, the arrows. In this case, I call delta the co-product and epsilon the co-unit. So you can think of a product taking 2 things, giving you 1, and a co-product takes 1 thing, gives you 2. Very easy. Okay, let's briefly talk about Sweetler's notation that was mentioned. So as we have said, the co-product of an element H is something in the tensor product. So we can write this as a finite sum over some Hi1 and Hi2. The 1 just says that it's in the first tensor, 2 just says it's in the second tensor. And then Sweetler says, no, this is much too complicated. Let's just write H1 and H2. And yeah, that's it. You basically hide that you are having a finite sum. And this will turn out really useful if you do complicated computation. Okay, let's have an example of a co-algebra. For example, take polynomials in X. Yeah, it's just very simple. This can be seen as a co-algebra with the following co-product and co-unit. Co-product of some x to the power n is just this sum here, where I sum over all xk, xn minus k with the binomial coefficient. And you can show that via the properties of those guys here, you get the co-associativity in this diagram. And the co-unit is very simple. It is almost always 0. It's just sometimes 1, namely when you plug in 1. And then you extend those guys in a C linear way to all elements here. One more example is the dual space of a finite dimensional algebra. With A, it's an algebra. You take a look at the dual space, and you take a look at the dual multiplication, which is now your co-product, and the dual unit, which is now your co-unit, just as it should be. So what is this dual multiplication? So, okay, you apply this to a functional, and you get something that is in the dual of A tensor A. This means you can evaluate this at A tensor B, and this is by definition just alpha of the multiplication of AB, so it's just alpha of AB. and you see that all the properties are of a co-algebra are satisfied.
So sorry, this assumption of A being finite dimensional is used in this identification of the dual of the tensor product with the tensor product of duals, yes?
Absolutely. This is crucial. Otherwise, this would not be correct, or you would need some other tricks. I mean, you can also modify the tensor product and avoid this, but for the sake of this lecture, let's keep it simple and look at finite dimensional algebra. Yes. Okay, so maybe the next complication in Sweetler's notation is written here. Looks a little bit scary, but actually is not. So what is written here, this first equation is just the diagram that is here. So just have a quick look at this. What is meant was, okay, you first, you co-multiply, you are ending up in H tensor H, and then you co-multiply the first tensor factor. And this should be the same thing as you co-multiply, and then you co-multiply on the second tensor factor. This is just written here. So co-multiply on the first tensor, and co-multiply on the second tensor. They have to be equal. This is co-associativity. So let's write this down in Sweetler's notation. So we start with delta H, which is just H1, H2. And now we co-multiply H1, so we get H11 and H12, tensor H2. And this has to be the same as H1, H21, and H22. And Sweetler comes and says, this is much too complicated, too many indices, I don't like it. Let's write this as H1, H2, H3. So we are hiding even more sums.
Oh, sorry, maybe a quick remark. So there is also one place in mathematics when one uses this similar notation, which is the Einstein summation convention. But the Einstein is easier since usually when we deal, for example, in differential geometry, the index over which we sum up is always runs through from 1 to n, where n is dimension. But here, those indices, those numbers of summands vary. So if you would like to keep track of all these indices, it's really a mess.
Absolutely. Thank you for this comment. Okay, and in a similar way, you can write even higher co-products here with even more indices. Okay, let's continue. So now we arrive at the definition of first a bialgebra and then a Hopf algebra. So a bialgebra is an algebra with a co-algebra structure such that the co-product and the co-unit are algebra morphisms. Okay, so this means, you know this, but just saying it out, this means those are unital maps satisfying those properties here. Yeah? So just algebra maps. And maybe here one should specify what is the algebra structure on the tensor product. This is just the tensor product algebra, meaning you multiply the first one with the first one and second one with the second one. Good. So this is an algebra, basically just saying that you have an algebra and a co-algebra structure, but they are speaking to each other. Yeah? It's not that they are independent. This is what this definition says. Okay. Secondly, we have our definition of a Hopf algebra. So this is now this guy here. We have a product, we have a unit, we have a co-product, we have a co-unit, and so that this is a pi algebra. And we have a special map S, which we call an antipode, such that this diagram here is satisfied. So this looks very scary, but it's in fact very simple, because if we use Sweetler's notation, we can write this diagram simply in this way. So what is happening is you co-multiply H, so you get H1 and H2, then you apply S to one of the tensor factors and you multiply this. So you get this here, and this should be the same as going through the middle, which means it's epsilon of H times the unit. Yeah, and so just for the moment, think of the antipode as some kind of inverse operation. We will see why this is a justified name to call it an inverse. So before looking at examples, maybe let's have this exercise here, which is very useful. So let's take a step back and look at an algebra A and a co-algebra H, and take a look at the linear maps, the C linear maps from H to A. So this we can structure as an algebra in the following way. So take two linear maps from H to A, F and G, and you convolution multiply them in this way. You first apply, so there's an H missing, sorry. So you first apply the coproduct so that you get H1 and H2, then you apply F, tensor G, and you multiply so that you arrive here. And the claim is that this is an associative unital algebra with the unit given by the composition of the co-unit of H and the unit of A. And as the exercise would be, you can prove that this is really true. If you have this, you can show that in the case you have an Hopf algebra, you show that the antipode is the convolution inverse of the identity map. So this means it's not the inverse as a C linear map, so really an inverse in the convolution algebra. What this also means, so it follows from this, that if you have an antipode in a bi algebra, you can only have one. This is what this exercise shows. Furthermore, you can show that any antipode is an anti-bi algebra morphism. So this means that it reverses the product in this way, maps the unit to the unit, and it reverses the coproduct, and it maps the co-unit to the co-unit. Just as a hint, if you want to prove the last one, use the convolution algebras here. If you solve this exercise by Friday, I buy you a beer. You can take a picture or ask me for the.
Sorry for the technical problems.
Okay, so let's try with the microphone here. Okay, so this is about the exercise. Good. So now it's definitely time to see some examples. So the first one. Okay. So the first one that I will give is the group algebra. So this is because I said on the first slide or maybe second slide that you can think of a Hopf algebra as some kind of group. And so this is the example to look at here. So take any group. I think all of you know what the definition is. If you don't know, it's written here. It's just some set with an associative operation dot and a neutral element E that has these properties here. such that for every group element, there's also an inverse group element, meaning that those equations are satisfied. If you have any group, take a look at the group algebra, CG, and call this H. So the group algebra is just a C linear span of G, meaning that elements of H are of this form here, where we sum over all group elements, and the KG are elements of C, where we want only finitely many of those to be non-zero, because we want a finite something. And the product is just what you might guess. So you can multiply two of those guys, simply multiplying the case and multiplying the group elements. And you have your unit just coming from the neutral element of G. So this is what the algebra is. So let's see that this is also a Hopf algebra. So by definition, on a group element, the coproduct is just doubling G, and epsilon is just setting it to 1.
So maybe a quick remark. If you consider this finite formal sum of group elements as a function of the group, and if you see what does this formula of the product means, it is precisely the convolution of the function. So it's quite nice to rediscover the convolution in this setting.
Okay, and the antipode is really just the inverse of the group element G. What you do afterwards is just you extend those maps that you gave the definition only on G as a C linear map to all of the group algebra. And it turns out that it is really a Hopf algebra, not difficult to show. Second example is the universal enveloping algebra. So you take a Lie algebra, which just as a reminder here, it's just a vector space G with some linear operation, which is skew symmetric and satisfies the Jacobi identity. And if you have such a Lie algebra, you build the universal enveloping algebra written like this as follows. You first take the tensor algebra that I hope you have seen in your linear algebra course. If not, it's just a direct sum of all tensor powers of G, and you multiply via the tensor product. You just build higher and higher tensors. And you get the universal enveloping algebra by modding out the ideal generated by those elements here. So you would like to set equal to 0, these kind of things. So you want the Lie bracket to be the commutator in the tensor algebra. And you can show this is an algebra with product given by the tensor product and unit coming from the unit of C. So even more, we want to show this is a Hopf algebra. And yes, you see on elements of the Lie algebra, this is done like this. You take this formula here, which means you see X as a primitive element. This is how people call this. Just X tensor 1 plus 1 tensor X. Epsilon of it has to be 0, and the antipode is just minus this element. And now what you do is you extend the first two as algebra morphisms, and the second one as an anti-algebra morphism. And we have to do this for the second one because we have seen in the exercise that S has to be an anti-algebra map. So this is the way to go to general element. Just as an example, what this means if you have X and Y in the Lie algebra, you say that delta of XY is just this, and S of XY is the same thing here, just with the elements flipped. And you can show H is a Hopf algebra. Third example, and I'm slightly running out of time, so I'm even tempted to skip this one, but it's very beautiful, so I don't want to. But yeah, maybe let me skip this because otherwise I think I cannot finish. Okay, so I'm just very briefly saying there are this is one of these Q deformations of a matrix quantum group. In this case here, SL2, and you have, so Q is some complex number that should not be 0 and maybe not a root of unity. You take the free algebra generated by alpha, beta, gamma, delta here, and you have some slight non-commutativity just given by this Q. You can write the coproduct, co-unit, and antipode in a nice way in this matrix co-multiplication form. But okay, I'm skipping this because I'm not. So just one theorem about Hopf algebras that I would like to mention is this one here. And so this basically says that you can think, you can identify your Hopf algebra with the modules of your Hopf algebra. So those two are kind of the same thing. And so how to make sense of this? If you have just an algebra, then a left A module of, left A module is just a vector space M with a linear map that we just write as this arrow that says that A acts on M. Action just means this. So if you first act with B and then with A has to be the same thing as acting with AB, and acting with the unit doesn't change anything. This is a left A module. So let's have a look at the category of finite dimensional left A modules. This just means that the underlying vector space is a finite dimensional one. We could also drop this, but then everything is slightly more complicated. And here in this lecture, I want to be basic. So let's have finite dimensional ones. So let's have here with a lower A, upper F just for finite. So a lemma you can prove, it's not difficult. If you have not only an algebra, but a Hopf algebra, then your left H modules have a lot more structure, meaning that you get a tensor product and you get a module structure on the dual. So what this means is, in formal terms, you get a rigid monoidal category, where rigid stands for the dual and monoidal stands for the tensor product. So what we have to show is that if we have some left H modules M, then also the dual module is a left H module, and also the tensor product is a left H module. This is how you do this. So you act on alpha, which is on the dual of M. You act on this by acting with the antipode on M. And you act on the tensor product by first using the coproduct on H and then acting on M and M. And this is an action precisely because S is an anti-algebra map and because the coproduct is an algebra map. You can see that this works. By the way, acting on the monoidal unit C is done via epsilon, via the co-unit, which is of course also an algebra map. So that's also an action. So there's this very powerful theorem that tells us that basically also the other implication is true up to some identification. But you can say that basically any rigid monoidal category can be understood as left modules of some Hopf algebra. And so how does this work? So the theorem says that, okay, take a rigid monoidal category C, take some strong monoidal functor. I'm not going to tell you what this is, but it's basically just a way to translate the tensor product of one category into the other one. And if you have only this data, you can find a Hopf algebra H and another strong monoidal functor G, such that you have this diagram here. And if you read this, this really just means that you can understand C somehow as the left H modules for a Hopf algebra H. And in some cases, your H is even nice because it might be very easy. And then you can show that those two are actually equivalent. Some nice cases. Let me just mention in one sentence. If you want even more structure on the level of modules, let's say you want a braided, rigid monoidal category. Braided meaning that you have a kind of flip operator. then this corresponds to more data on the Hopf algebra level. Namely, this is what a quasi-triangular Hopf algebra is. So here the credo is somehow that information on the level of modules corresponds to information on the Hopf algebra level. That's a very powerful thought. Good, so this was the first part. Let's see. So now about the forest and trees. Yeah. So let's start with what is a rooted tree. And there's this very genius definition that says it's a tree with a root. And I really like these kind of definitions that give you nothing. So a tree is a planar, connected, simply connected finite graph, and the root is a distinguished vertex. So what all of these words means is maybe best understood by just looking at trees. So those are trees. Yeah. So you can have just one vertex, you can have two vertices connected, and then build more and more complicated trees. For example, for this one here, it does not matter if the taller one is on the left or on the right. Or for us, this will be the same tree. And we also take the empty tree, which will be our unit tree. So out of those, you can build a algebra. Let's call it H. So take the pre-Q algebra generated by all those trees. And we don't want to care about order. So we take all the non-ordered sets, which corresponds to a commutative algebra. So
sorry, what is the reason for working with Q coefficients and not R, for example, or
yes,
C?
That's a good question. I don't know the deep reason why you take Q and not R, but in the paper of Kohn and Kleimer, they stick to Q usually. So I cannot give you a good reason. I'm sorry, but let's for the moment work over Q.
Okay.
And yeah, so just here you see the photograph of Cayley, who introduced these rooted trees. Okay, so just to be clear, what is this algebra structure? First of all, elements of the forest are now of this form here. This is an element of the forest. So you have some rational number, you have some non-ordered set of trees, and you can add and subtract them. So that's really as easy as it looks. And you can show this as an associative unital algebra with multiplication that just takes multiplies the rational numbers and builds the set out of the single set. Yeah, so we just take those sets here, make one set of a combination of those.
So sorry, for example, if one element in this set of multiplied trees is the same, we will repeat it, yes?
Yes. Or you can write a 2.
Ah, okay. Okay.
Yes, and it's easy to see that you have commutativity. Yeah? And okay, the unit element is just the empty tree, so the empty set. Nice. So the forest is an algebra. Even more, it's a Hopf algebra, and this is a picture of the coproduct. This is how you should think about it. What does it do? You take a tree and you sum over all possible ways on how to cut a tree. And since we know that we have to end up in the tensor product, so we have two parts here. The first part is the part that we cut, and the second part is the leftover part. So let's see this in an example. So here's the formula. And let's apply the coproduct on this tree here. So all possible cuts. First, the most lazy cut is the not cut. So we don't cut and leave all of the tree. Second thing that we can do, we can cut here. So we get just one vertex tree here, and we are left with this tree. Second possible cut is we can cut here. So we are left with two identical ones on each tensor side. We can also cut here, which gives this, and then it's leftover this very tall tree. We can have two cuts at the same time, so we can cut here and here, which gives you two single vertex trees, and we are left with this tree. We can cut this and this. So we have as the trees that we cut those, and we are left with just a one vertex tree, and we can be very brutal and cut everything. So we have all of the tree and nothing is left over. That's the co-product. So if you have this, you can.
Excuse me,
Yeah, please.
maybe could you explain what happens if there is more than one cut? Why there are grouped this way? Like it's
Sure. So if you, for example, in this case, or let's say this case because it's the most interesting. No? In this case, what you do is you cut here and you cut here. So you can do several cuts at the same time, but you cannot cut things that are already cut. So if you have like, if something is cut, you're not allowed to cut it afterwards. Yeah?
okay, thank you.
And then yeah, you just group it here in as an element of the forest that we have seen. It's just these sets of trees, and that's how you do this.
Okay, so may I ask, so is it possible to have 3 cuts and have like one group of 3 points in this
Absolutely.
in this co-product, because it's not
So for this one, not.
Yeah,
For-
because you have only 2 branches. So
okay.
you could have 3 branches and then you have 3.
Exactly. Okay, and then for the algebra, so for let's say you have the product of 2 trees, T and K, and multiply it with some rational number, then you just say this co-product is given like this, and this is what it has to be, since we know that the co-product has to be an algebra morphism, so it's very natural to extend it in this way here. So also to give you an example that I'm probably not able to calculate through because of time reasons, but you can see, so if we take the co-product of this one, it's really just put out the number and co-product on this one, co-product on this one, and then multiply the tensor factors. So this is how you calculate more complicated elements of the forest.
So sorry, just to ensure myself whether I understood it correctly. For example, if we choose this left branch, yes, it consists from 2 vertices, sorry, 2 edges. So we are not allowed to cut the first and the second of the first branch, left branch, or we are not allowed to do
You're
this.
not allowed, yes.
So since we already cut it once, we cannot cut it twice.
Absolutely. Very correct. Yeah. This
Okay.
is the rule.
So no, I don't know whether it is right to call it that by sub-cutting the part which was already cut.
Yes, so I briefly mentioned that you're not allowed to cut something that you already cut. So
Yes, but if the something is a single edge, then it is clear. Yes, we are not allowed to cut twice the single edge. But even if it is more complicated, so still you cannot do this. Yes.
you cannot do this.
So for example, for this whole left branch, which consists of 2 edges, if you cut it once, you don't touch it anymore. Yes.
Exactly.
Okay. Thank you.
Yes. As you can see here in this co-product, you don't have the on the left-hand side 3 of the single vertices. This would be what you were asking. This is not allowed. Okay, those are the rules, and I mean it looks nice, but I mean it's so for me it was very hard to see that you can get any meaningful thing out of this. It looks like absolute chaos, yeah, but it was proven by Kramer and then Kramer that this operation is co-associative. So you really have this property, and that's fascinating how to prove this. It's seems to be very complicated, but it's true. So it was nice. And also note that we don't have co-commutativity, meaning the opposite co-product is not the same as the co-product. And this we already see in this example here, because, for example, this tree does not appear on the left. So if you flip, you get something different. Which the co-unit is relatively easy. So it's almost all times just 0. Only on the empty tree it gives you 1. And then it's quite easy to see that the co-unit axiom is satisfied. It was one of those diagrams of a co-algebra. And this you can easily see. So if you apply epsilon to, let's say, the first tensor factor of a coproduct, you want to get your tree back. And you can see, okay, epsilon here is just 1, and you have your tree. And in all other instances, you have something on the first tensor. So this gives always 0, and you are really left with the tree that you started with. So this shows that this holds. And okay, what turns out is you can show that the Hopf algebra is not only a co-algebra, it's even a bi-algebra. And this is kind of the way that we built it, because the coproduct and co-unit are by definition algebra morphisms. So this is easy. But it was shown by Kohn and Kreimer that we have even an antipode. So the forest of rooted trees is really a Hopf algebra. And you will see the antipode on the next slide. And I just want you to note that we have commutativity, but not co-commutativity. So let's see the antipode or the inverse tree. We know that the antipode should be an anti-algebra morphism from H to H, and it should map the empty tree to the empty tree, the unit to the unit. Okay, so we give a recursive definition in this way. On the one vertex tree, we just say it's minus this tree. And then on any more complicated tree, we give this definition here. This means take the same tree with a minus sign, minus sum over all reasonable cuts. I will tell you what is a reasonable cut of S of the tree that we cut times the leftover tree. Now a cut is a reasonable cut if it's not the total cut and not the no cut. So all cuts that actually do something and not cut all of the tree, they are reasonable cuts. Good, let's see it in examples. So if you take this small tree here, by definition, it's first minus the tree. And then the only reasonable cut that we can do is cutting once here, which we are left with 2 single vertices. And we have calculated that S of the single vertex is a minus. So this is why this minus becomes a plus. This is the antipode of this tree. Maybe briefly, let's have a look at this one here. So antipode is minus the tree. One reasonable cut is cutting here or cutting here. So we can do this twice. This is why we get a 2 here. And we get this one vertex here, and the leftover is this tree. Or we can cut both at the same time. Then we get S of this set here. And okay, those, since we know that S is an so this is minus this, and S is an anti-algebra morphism, we are left with this here. So this is the antipode of this one. And we can check.
Sorry, you said that this S is defined recursively, so you have some grading, yes, on this set of rooted trees. So.
Yes, so here I'm kind of vague. So I hope it's kind of intuitive how to see that, how to have growing trees that are getting more and more complicated, and you define this on more and more complicated trees.
Would you agree that we can speak about the length of the longest branch? And each
Sure.
time you make a cut, a reasonable cut, you must diminish by 1
Yes.
the length.
Okay. So probably via the length, so it's a good way to say what are more and more complicated trees. Okay, so since I don't have much time, I don't give you the computation here, but you can look it up for yourself. So here just this antipode axiom really holds. So you can see that S, at least for this tree here, has the correct property. And then you just have to go to the paper of Kohn and Kreimer, or trust them, that this operation really gives you a Hopf algebra. So this works for any tree. Very nice. So now what to do with this? We can use the Hopf algebra of rooted trees to talk about nested integration. So I don't know, maybe this is in the holiday spirit since we have August. It's Christmas is very far, but let's decorate our tree with some beautiful one forms. So it looks like this now, where the omega i's are some functions, and yeah, just take the differential form in R like this. And okay, so how does this correspond to a nested integration? Like this. So we say that the nested integral corresponding to the tree T looks like this. So you first integrate over the omega 1, and then everything that is connected to omega 1 is also integrated there. But for example, the integration for omega 2 is only considered for omega 2, but and also for omega 4, but not for omega 3, since this is not in the branch of following omega 2. Okay. I don't know if this was clear. I'm running out of time. So this is for nested integration. Yeah. Well, just 1 minute about Feynman diagrams. I'm absolutely not an expert on these things, so please just take this as some motivation. It's what I'm going to say is absolutely not rigorous. So I hope that everybody has a vague understanding of what a Feynman diagram is. It's something that looks like this. For example, here is depicted electron-positron annihilation. So you see it's an electron and a positron, and they give you some photons here. And so those diagrams in physics correspond to, in general, divergent integrals. What people want to do, they want to renormalize this. So they want to remove the divergences. And this can be done in a first step by looking at subgraphs with subdivergences. Now the connection to trees is that you can find a decorated tree corresponding to the subgraph structure of such a diagram here. And then this decorated rooted tree corresponds to some kind of nested integration. So let's look at this example here that is taken from Kohn-Kreimer. So you have all of the graph. This is corresponds to the root. Then you can take a look at the subgraph here, which is forgetting about this part here. And you can look at this subgraph here, and they are nested in this kind of way. So just a straight tree. And what is not written here, but what we see on the next page is that to this vertices correspond some forms, which then correspond to a nested integral. And the forms and integrals are those. So take some epsilon bigger than 0 and take a look at the following ill-defined integrals. So they are all infinite. And you can somehow see how this works. So you start with a very basic one, and then you see them as nested integrals in this way. For the 2 tree, you have a 1 tree integral hidden here. For the 3 tree, wow, you have a 2 tree hidden here, and in this way you would have 2 of them in this way. So this is kind of in a very short time how to understand this. Now, how to use the Hopf algebra structure to renormalize this? Let's have a look at the 2 tree, and the R means renormalize. What you do is you fix a renormalization scheme. Those are those brackets here, and I'm going to tell you very vaguely what this means. You take the coproduct, you apply the antipode to the first tensor and the renormalization scheme to the first tensor, and then you multiply. So in this computation, what you get is this. And Kohn and Kreimer tell us what you get is something fine. It's magic, it's really beautiful, but this is how it works in some of the toy models. So I mentioned the renormalization schemes, so they can be all kinds of things. For example, you can have it on shell, which would correspond simply to fixing it at the unit. You can have some minimal subtraction scheme, which corresponds to the pole part, and many more complicated things like BPH, Z, renormalization, but I don't have time to go into this, and I'm also not the correct person to ask these questions. This should be asked to physicists. But yeah, the take-home message here is just what I find absolutely mind-blowing, is that something as mathematical like the Hopf algebra structure of the forest appears in quantum field theory and can actually help to organize those nested integrals and tell you how to renormalize. I find this absolutely mind-blowing. And yeah, with this message, I think I stop. Thank you for your.
Thank you. Okay, so do we have any question?
Okay, so may I ask about the last topic you talked about? So maybe first that you talked about Feynman diagrams. So maybe could you elaborate how trees, especially rooted trees, are obtained from any diagram, especially those which are not trees, because those need renormalization.
Mm-hmm. Yes, so I think this slide here is helpful. So the tree really corresponds to the subgraphs. Yeah, so you have the root, which means it's all of the graph, and then there are certain ways to find suitable subgraphs. Yeah, and then the subgraphs corresponds to other branches of your tree. Like here, you can see so this vertex corresponds to the subgraph here. That is only part of all of the Feynman diagram. And this one here is just the smallest one. So really the tree should be thought as organizing the subgraph structure of the Feynman diagram.
Okay, so and may I ask, so for example, composing diagrams or something like that, the co-commutative structure and this division with respect to cuts would correspond to considering all subdiagrams.
So your question is, if you compose Feynman diagrams, how does this translate in Hopf algebra language?
Yes, and especially if this.
So I would say, since we have seen that the forests are just the unordered sets, I guess really the composition of diagrams should correspond to the fact that the coproduct is an algebra map. So you can look at them separately, and then probably you have to multiply in the tensor product in a suitable way. But this is, I guess, I don't know the answer to your question.
Okay. And may I ask if you can say maybe a few words more about the renormalization that you talked in the end. So maybe to get an idea of what the expression.
Yeah, so I feared that question because I'm absolutely not qualified to talk about this. But okay, so what you do, you have to look at those integrals, yeah, and you somehow have to figure out how divergent they are and what parts are kind of the messy ones, yeah, and you want to treat them separately and remove kind of the divergencies corresponding to the sub-divergencies. And so you're asking me how to do this. Yeah, you have to subtract the parts that are too large, that you're ending up with something finite, but the exact way that you do this, you have to speak to physicists. I'm not qualified to motivate this.
Okay, thank you.
Okay, do we have more questions? So maybe I would like to ask a question related to the previous question of Bartek's. So as far as I understood in physics, the most nasty divergences are those coming from the diagrams which have many loops. And somehow in this story with rooted trees, I don't see any loops. Yes, those are trees. So
yes, while maybe so what about this? it is true that you don't see it in the trees, but of course, trees should not be loops, that the trees should correspond to the subgraphs. So you could think of some subgraphs that have only some of the loops, not all of them. And then maybe this can be written in terms of a tree.
Okay, so somehow those loops are hidden in the vertices, yes? So we
Yes.
do not look so closely, okay? And if we look closely, then we could see those loops.
I would guess so, yeah.
Okay,
But
and
as I
also,
said, all of this is not rigorous. I'm a mathematician, not a physicist.
okay, and also one more question related to those integrals. All those integrals which you have written are one-dimensional integrals. So this corresponds to a theory which takes place in one dimension, one space dimension, yes?
Absolutely, absolutely. This is a toy model, yeah.
Okay, so in the four-dimensional case, you would have your integral over something four-dimensional, yes?
I guess, yeah.
And this is already Euclidean, yes?
But I don't know how to do the more complicated ones. If you want to see some hints, really go to this paper. It's very well written. But the toy model that they calculate through is this one here, just the one dimensional.
Okay, thank you. Yes, please, Piotr.
One quick comment, because it starts right from here, from Kohn-Kreimer. The following work was by Kohn and Moscovici, about their Kohn-Moscovici Hopf algebra for foliations.
I'm very sorry if I don't give the correct credit. So then, okay.
No, credit is correct. The thing is that somehow allow us already in this mindset of working hard with Hopf algebras. And then it turned out in their studies of non-commutative geometry of foliations, it turned out that to compute things, it is very useful to construct out of very complicated geometry of foliations, is to construct a Hopf algebra, which is way more complicated than Kohn-Kreimer Hopf algebra. In particular, is non-commutative, not only non-co-commutative, it's non-commutative. And this is how they discovered Hopf cyclic homology. And this was quite a revolution in cyclic theory, and it came from this Hopf algebra. Next.
Okay, and I think that the motivation was to somehow organize the very complicated computation. So the similar story as in this
Exactly
normalization business.
Yeah,
where
exactly, yes.
Very complicated computation, and you would like to see some structure in this terms.
It turned out that in order to detect some characteristic classes, they could work with Hopf cyclic homology of this crazily complicated but absolutely tangible Hopf algebra.
I mean, this is really genius, I would say, like looking at those kind of things and saying, yeah, sure, this has to be a Hopf algebra. I wouldn't have been that brave to say it has to be true.
It's like hiking in a forest and seeing a coproduct.
Yeah, exactly.
Okay, I have one more question. So above all those Hopf algebra, there is some special universal Hopf algebra, which is somehow related to the thing called cosmic Galois groups. Could you say something about it? Something even more universal than this algebra of rooted trees.
I have to confess that I don't know the universal Hopf algebra. What is it? I don't know.
It's somehow related to the thing called universal cosmic Galois group, and this is defined as a universal enveloping algebra of some free Lie algebra with graded free Lie algebra with generators in every integer degree, something like that, okay. And dual of it, okay. And then some semi-direct product.
This is universal in what sense? So that for every Hopf algebra, you find some kind of map from the universal one to the Hopf algebra?
Maybe not for any Hopf algebra, but for any Hopf algebra of Feynman diagrams or graphs. You have homomorphisms from this universal one to the particular corresponding to the particular theory. Since for every physical theory, you get Hopf algebra related to this particular theory, but above all, it's this universal, which maps to all of physical theories.
Interesting. Thank you.
Actually, I have one more question. I'm looking at this antipode formula. Is it obvious that this antipode is bijective?
Good question. So I guess it is because
Yeah, I guess
I only know one Hopf algebra that doesn't have an invertible antipode.
and it's not this one.
And it's not this one, yeah. Is it obvious? I don't know. I haven't thought about it, but from the formula, I would say nothing here is very obvious. You have to start maybe.
Yes, it's a recursive formula.
Yes, so you have to start with easy trees and then see if you can say something about more.
And how about a squared? Again, I bet it's not identity.
Probably not. So this maybe you can even see on very simple trees. So
Exactly, yes.
If
That
you,
should
if
be
you take even this one and you apply it again, you don't get the identity, I'm pretty sure.
Okay, thank you.
Okay, and sorry, could you please go back to the last slide, probably the last one? Yeah, this one. So once you introduce this Hopf algebra of rooted trees is fixed once and for all, and then you have written that above we have to fix the renormalization scheme. So this Hopf algebra does not depend from the renormalization scheme, yes, or is it?
No. So how I understand this is a way to organize renormalization schemes. If you have one that is suited for your model, then the Hopf algebra of rooted trees just tells you how to apply it in which way. And you can see, so this is really those brackets here. And you see they're always on the left side, and you have to apply them in this way: antipode, coproduct, multiplication.
Okay, so this formula gives using this square bracket gives you a general form, and then those brackets means different things depending from the renormalization scheme. Yes?
Absolutely.
Okay. Thank you. Okay, some more questions. Let me see if there are some questions on the Zoom, but I don't see any raised hands. So I think it's time to thank our speaker again. And I will stop recording.